Okay, it's time for the last chapter, 15, about climate and climate change, and our driving question, how and why does climate change? So we've talked a little bit about climate over this summer session, over the semester. Climate is the weather of a locality that's been averaged over time and through the extremes. Climate varies spatially and temporally, and it's described quantitatively, numerically, through things like normals, means, extremes, and so on. NOAA's National Climatic Data Center, the NCDC, is responsible for processing weather data and creating the numerical values that we use, the normals, the means, and so on, and providing that data to the public. I spoke with you already about the climatic norm. A normal is a 30-year average for some particular variables such as temperature, precipitation, air pressure, and it can vary. It can be an annual normal. It can be a normal for Arizona for the month of July. Whatever the case, it's a 30-year average, and the 30-year time period is updated regularly. So we're looking at the past 30 years in 10-year increments. Anomalies are departures from these normals, from these long-term climatic values. Positive anomalies mean that they are above the averages. Negative anomalies mean that they're below the averages. We typically look at temperature anomalies, but we can also look at precipitation anomalies, though they are more complicated due to spatial variation in precipitation. This picture shows precipitation anomalies, and you can see just from the pictures how complicated the patterns are. On the left, we have a long-term average of precipitation for December 2011. So these are average precipitation values, and you see here the color chart that shows the percent of normal precipitation. So these are percentages, and it's normal when it's kind of right between the yellow and the green. So if it tends toward purple, it means it's above normal. If it tends towards red, it means it's below normal. So we can quickly see the areas that are a little bit drier and wetter and so on for the month of December. And then on the right, we have temperature for the long-term average, the period between 1981 and 2010 for December 2011. So again, we can look at the departure from normal. The closer it is to red, the more extreme heat, warmer than normal, and on the purple end, we have colder than normal. So you can see the difference between the patterns in precipitation compared to temperature for December. It's important to have an understanding of how global patterns vary for different variables. Here we're looking at mean January air temperatures, and you can see the isotherms on the map show the temperatures in degrees Celsius. You can see with temperature they're pretty much stratified latitudinally, but then there are some big jumps that run longitudinally, up and down. These tend to happen over land masses where there's an extreme in what's happening. So here in South America, the Andes Mountains run down the western coast of South America, and you can see how that affects the temperature regime. Here we have mean July air temperatures. And here we have mean annual precipitation amounts in millimeters, total precipitation for the year in millimeters. So when we have a sense of these patterns, we have something to compare it to. We talk about climate normals so we can have a baseline to compare. When we look at climate change, we can vary our scale in time and look at geologic time, which goes back thousands, tens of thousands, even millions of years. And here you see a graph that shows the eons, eras, periods, epochs, and millions of years ago. And when we look at the climate record for these times, as far back as we can, we look at data that have been collected through ice core samples, through tree ring analysis, through the geologic record, the different rock that is underlying us. We often see evidence of a very different climate where we live compared to what we have now. And so we know that the climate has changed drastically on a geologic timescale. One of the drivers of a geologic climatic change is the fact that we live on a shifting Earth. We have plate tectonics, so the tectonic plates are moving around. And here you can see the evolution in geologic time of how the plates or continents are now. It's believed that they were once all kind of grouped together in this supercontinent called Pangaea, which slowly began to break up and the plates spread out to what we have in the present day. So as these different land masses move to different places on the Earth, they are subjected to different amounts of solar radiation. It changes the dynamics of what's happening with the weather, and we get climate change. Here is a glacial ice maximum, and we see in North America that about 20,000 years ago, much of North America was covered in glaciers. So we were in an ice age period. So you can read in the textbook how the Earth fluctuates between these glacial and interglacial periods and how that affects our weather. Some of the causes of climate variability are shown in this picture with different interactions that take place. Interactions between things like the land. Changes in the land cover affect the albedo, affect the vegetation, and all these have effects with how that land interacts with the atmosphere. Changes in atmospheric composition from different chemicals that are maybe released through volcanic activity or just outgassing, dust particles, and so on. When we look at the water here, we have a lot of potential changes. There's interaction between the air and the ice. There's interaction between the ice and the ocean, and so on. All of these things change and affect the climate of the Earth. This graph shows the variation in the mean annual sunspot number. So solar activity. It's believed that there's a relationship between solar activity and Earth's climate. Though we don't understand that at this time, it does seem to be the case. And you can see the sun goes through regular periods of activity and inactivity. And then the Earth's movements itself. There are three primary movements that the Earth makes. One is the orbit of the Earth around the sun, and the orbit changes a little bit. The eccentricity of that orbit varies on long time periods. We have another movement of the Earth, which is the rotation on the Earth's axis. That axis can be tilted. So we have a tilt now of about 23.5 degrees, but that tilt can be more or less on a longer time period. And then finally, we have the precession, which is the wobble of the Earth on its axis. Right now we're pointing to our pole star as the North Pole, or sorry, the Polaris, the North Star, and that's not always been the case. In longer astronomical time periods, it's known that the Earth's axis was pointing to a different pole star, and we call this movement precession. So when we look at these changes over long periods of time, the scale here is thousands of years, we can see the eccentricity of the orbit has changed. We see the precession of the Earth has changed, and also the tilt of our axis has changed. So you see different values here. For the tilt, it shows the actual latitudinal, or sorry, the degree that it has varied by. For precession, we see the Earth-Sun distance in June. So how far is the Earth from the Sun in the month of June? And then for eccentricity, we measure it as a percentage. Other things that affect the Earth's climate are volcanoes. So when we have a large volcanic eruption, there's a lot of sulfur dioxide that gets thrown up into the atmosphere, and it affects the Earth's climate. It can interact with water vapor and create droplets of sulfuric acid, and sulfate particles, sulfurous aerosols that can stay up in the stratosphere. They're ejected way up into the stratosphere, and they can interact with the ozone layer and change our climate. Here's a graph that shows large-scale volcanic eruptions and how the temperature of the Earth is usually a little bit cooler right after those volcanic eruptions. So here's one from 1963. We see a few years of below normal temperatures. Here's a El Chichon eruption from 1982. There we didn't really get a cooler temperature. But for Mount Pinatubo, if any of you remember that eruption from 1991, we had a couple years of lower temperatures. And then there's human activity that can affect climate change. And this can happen through the modification of the landscape, clearing out forests, building urban areas. We know that this changes the climate of the area. It affects the radiative properties of the Earth's surface, and that affects the temperature and precipitation patterns. Combustion of fossil fuels alters the concentrations of gases and aerosols in the atmosphere. We've had a rapid rise in CO2 concentrations in the atmosphere with the start of the Industrial Revolution. Rising concentrations of CO2 enhance the natural greenhouse effect to create what we call an enhanced greenhouse effect that contributes to this idea of global warming. And then we have the rise of other infrared absorbing gases that also enhance the greenhouse effect, gases like methane and nitrous oxide. This graph shows human-induced climate forcing. Climate forcing refers to the forcing of temperatures, typically increasing temperatures, or they're being forced because of activity. So here we have radiative forcing terms, so long-lived greenhouse gases, and we can look here and see that we've had a whole lot of CO2 and methane and other greenhouse gases that we've put into the atmosphere. So this is human-induced, and this has an effect on temperature to make the temperature warmer. With ozone, we have stratospheric ozone, which helps to cool the planet and prevent us from being bombarded with dangerous solar radiation. We also have tropospheric ozone, which is a pollutant that traps heat. So again, a warming effect. There's stratospheric water vapor from methane, another warming effect. And you can go through and see these different effects that we've had, and the net effect is that we're causing it to warm up. The radiative forcing measured in watts per square meter is about 1.5. The scientific consensus is out. The vast majority, 97% of the world's scientists, climate scientists, agree that yes, climate change is happening, and yes, it is caused in large part by human activity. Here is temperature data that goes back from 1880 from various organizations around the world, and they all show the same thing, that the last 20, 30 years or so have been marked by rapidly increasing temperatures. So when we look at what happens in the future, we look at our global circulation models, or GCMs, which you can read about in the textbook, that show the projected temperatures based on conditions that we know now. There's lots of different models, and they're shown in this graph by the different line symbols, but they all show that temperature increases in the future. It's just a question of by how much. So what's it going to look like? Well, a typical sort of estimate of our climatic future is that we're going to have enhanced greenhouse effect and global warming. So the current concentrations of our greenhouse gases will cause global warming to continue through this century. Our climate models predict that over the subsequent 20 years, the global mean annual temperature will increase about 0.2 degrees Celsius per decade. Even if greenhouse gas emissions stabilized at their present levels, it would not be enough to prevent this from happening. Other potential impacts are the shrinking of glaciers and the subsequent rising of seas. So this is happening. Our glaciers are melting and the sea level is rising. And a rising sea level is going to displace millions of people. It will have detrimental effects on livestock and really our way of life. Here are some pictures that show melting glaciers. So here's a 100-mile long rock-floored ice stream. So you can see we're looking at ice. It looks like a river, but this is all ice. And when we take a look at these glaciers in more detail, you see how they're melting. You can see here a meltwater lake, and then here is a glacier that has this melting happening. So it creates kind of a lake that just eats through the glacier, causes holes throughout the glacier, and eventually it loses its integrity and the whole thing just breaks apart into the ocean. So people, livestock, and crops rely on freshwater runoff from mountain glaciers and ice fields. If we don't have the glaciers, we don't have the fresh water. We don't have this input of fresh water. Here's one example of a glacier, the same perspective since 1938 through 2006. You can clearly see how that glacier has broken up and is essentially gone. This could be any glacier anywhere in the world. They're all undergoing the same kind of behavior. Potential impacts here in an Arctic environment. When you shrink the Arctic ice, it triggers this feedback system. So we get warming up at higher latitudes that causes the sea ice cover to shrink. The albedo changes. We go from having a bright white kind of snowy surface to a much darker surface, so a lower albedo, which means more energy is being absorbed, and that's only going to cause more warming. So this is an example of a positive feedback. Not positive in the sense that it's encouraged or, healthy behavior, but positive in the sense that we start off with something and the net effect, as we follow through the cause and effect, is to reinforce that original thing. It's a positive feedback. So water supply is a problem in arid and semi-arid regions like Arizona. We're already having severe drought. We don't hear a lot about this in the news or in our local media. You kind of have to go out of your way to educate yourself. But we do have water problems in the desert already. And that's anticipated to get worse. Higher temperatures and more frequent drought problems will affect our food supply. We're already seeing food prices begin to rise. And there's a possible concern for an increase in hurricane intensity with this path we're on for climate change.